You know how your phone can finish your sentences for you, or how a search engine just seems to know exactly what you're looking for? Well, it's not magic. It's all thanks to some incredible technology that literally teaches computers how to speak our language. And today, we're going to pull back the curtain and see exactly how it all works.
It really all boils down to this one fundamental question. I mean, our language is just full of subtlety, emotion, and context. But computers, they think in pure, cold, hard numbers. So how on earth can a machine ever really grasp the meaning of a simple sentence, let alone something complex like a poem?
And right here, this is the heart of the challenge. On one side, you've got us, with our messy, beautiful, and often ambiguous language. And on the other, you've got machine language. It's all about structure and math. The thing is, most AI algorithms, they just can't handle plain text. They need numbers. It's the only language they speak. So how do we bridge that gap? Well, that's where this brilliant concept called word embeddings comes in. Think of it like a universal translator, a key that lets us turn our rich, colorful words into the numerical format that these powerful algorithms can actually work with and learn from. Okay, so how does this translation actually happen? Well, it all comes down to the magic of something called vectors. But don't let the name intimidate you. In simple terms, we're basically going to turn words into points on a map. Seriously. Let's just define that real quick. A vector, it sounds complicated, but it's really just a list of numbers. That's it. It's like a set of coordinates that tells you where something is located in space. Still sounds a bit abstract, I know. So let's make it way more concrete. Okay, think about cities on a real map. We can describe Vancouver with a vector of two numbers, its latitude and longitude. A computer can look at those numbers and easily find other cities that are physically close. But here's the cool part. What if we add a third number, a third dimension, like population? Now, a city's similarity isn't just about location. Suddenly, Seattle with a comparable population becomes a much closer match to Vancouver than some tiny town right next door.
So, if we can do that for cities, what if we could do the exact same thing for words? Just imagine this giant, multidimensional map where every single word in the dictionary has its own unique set of coordinates.
And this is the absolute key. In this giant word map, words that mean similar things are placed right next to each other. So happy would be neighbors with joyful, and sad would be really close to unhappy. The distance and even the direction between these points actually capture the relationships between the words.
And this is where it gets absolutely mind-blowing. You can literally do math with these relationships. Get this. If you take the vector for king, subtract the vector for man, and then add the vector for woman, you land almost exactly on top of the vector for queen. It's incredible. The map has learned to abstract concepts like gender and royalty all on its own. So that's just amazing, right? But how in the world is this map even built? It's not like a person is sitting there plotting all these points. Nope, it's built by a machine learning model that's been trained to understand one thing and one thing only: context. Let's see how that works. So here's the high-level view. You feed a model a massive, and I mean massive, amount of text. Think all of Wikipedia. The model then uses what's called a sliding window to look at just a few words at a time. Its only job is to get really, really good at predicting a word based on its neighbors. Every single time it gets a prediction wrong, it adjusts its internal numbers, those vectors, just a tiny bit. Over and over again, millions of times, until words that appear in similar contexts naturally get clustered together on its map. Now, as you can imagine, there are a couple of different ways these models can go about learning all this. So let's just briefly touch on the two main strategies. The first approach is all about frequency. It looks for words that are a dead giveaway for a certain topic because they show up a lot in one document but are rare everywhere else. You know, like the word cappuccino is a pretty big clue you're reading an article about coffee. The second and more modern approach is prediction-based. This is what we were just talking about. The model learns a word's meaning from its buddies. It sees dog next to bark, wag, and tail so many times that it figures out, hey, these concepts are all deeply connected. Okay, so this is all really cool tech, but why does it matter to you? Well, because this technology is quietly running in the background of so much of our digital world. Let's take a look at where you're seeing this every single day. Word embeddings are the secret sauce in spam filters that can actually understand the meaning of a sketchy email. They're what power those recommendation systems that suggest products that are freakishly similar to what you just looked at. I mean, ever wonder how your streaming service knows exactly what movie you want to watch next? This is it. It helps chatbots understand your questions, it enables machine translation, and it can even pull out names of people and places from a huge block of text. This isn't science fiction, it's the foundation of modern AI.
But there was a big problem with the early models. We all know that words can have totally different meanings in different situations. And fixing this problem led to the next giant leap in language AI, context.
This example just nails the issue perfectly. The word bank means two completely different things in these sentences, right? So how could one single point, one coordinate on our word map possibly represent both a financial building and the side of a river? See, the early models gave bank just one single fixed address on the map. That's it. But the newer, much more powerful models like transformers, yep, the tech behind ChatGPT, they do something incredible. They create contextual embeddings. They look at the entire sentence first and then generate a totally unique vector for bank right there on the fly, tailored to that specific meaning. This was revolutionary. This is how conversational AI finally started to grasp nuance. And just to give you a sense of scale here, we've been talking about maps with maybe 2 or 3 dimensions, something we can actually picture. In reality, these word maps are insanely complex. A typical word embedding can have hundreds of dimensions, which allows it to capture these unbelievably subtle relationships between words, like tone, formality, and even sarcasm. So the takeaway is this. We've gone from a simple problem of how do we feed words to a computer to creating these vast, complex, context-aware maps of meaning. Word embeddings have absolutely fundamentally revolutionized how machines understand us. And that leaves us with a pretty fascinating question to chew on. We've managed to teach a machine to understand the complex relationships between words. But what comes next? What happens when it truly understands not just the words, but the ideas, the emotions, and the intent behind them? The journey, it seems, is far from over.